Our next topic is Laplace transformation. In calculus, you've learned that you can use derivatives and integrals and transform. Okay? Really what you're doing. You've learned that you can take these operators, transform a function into another function. Take the derivative, and you get a new function. The transformation. Well, in this section, we're going to look at what is called Laplace transformations. And the reason we're going to go through this process is because we're going to use this to help us solve differential equations. And the process is going to be this. You have an unknown solution. You're trying to satisfy the differential equation, initial conditions. Okay? And we've had lots of problems that way. Well, with Laplace, what you will do is take your differential equation and apply Laplace transformations, that squiggly L there, and now you have transformed the differential equation, and it's now an algebra equation. Okay? So we're trying to solve for y of t, little y of t. So now we've got, they're using the term big Y of s, sometimes we'll use f of s, a function of s. So we started with a function in t, applied Laplace, and now we have a function in s. Just like we've done with derivatives, you take a function, and when you do it, you get a new function. So once you have that, right, you need to try to solve this new transformed function. Okay, we're going to solve it in terms of, in this case, we're using s, but it could be any letter. But we're going to solve this algebraically. Right? Now we have solved for y of s. Right? So we then are going to do the inverse Laplace transformation. Okay? Just like we did derivatives, and you got a function, do an integral, you get back to your original function. Well, that's the same idea here. So Laplace inverse. And now you have a solution. You now have y of t, of the original initial value problem. And the question then, is that a good solution? If not, it has something to do with the initial conditions. We might have to go back and start over again and do it. But there's the process. It's trying to solve for y of t. You have a differential equation. Apply Laplace, and you now have a new equation, but it's algebraic. So you solve it algebraically, and now you do the inverse Laplace, and we have our result. That's the technique. That's the way we're trying to get there. So we've got to start out with, what is Laplace? Right? What is Laplace? Well, here is the definition. Right? You have some function defined on some variable, we'll call it t. T is greater than or equal to 0. That's got to be a condition. Then the integral, here's the integral. Laplace, when you work on f of x, what you get is an integral, an improper integral, from 0 to infinity, e to the minus st, the t value that's right here, f of t, whatever that was, dt. This is said to be the Laplace transform of the function f, provided that this integral converges. Provided that that interval converges. So when the defining interval converges, the resulting is now a function in s. And so if you have a function in t, and we do a Laplace, it's called a linear transformation, you get a function in s. And that will always happen. You have a function in t, take the Laplace, you now have a function in s. Okay? Now, this is the definition. Okay? We already know from all the calculus that we do along the way that that's not how we want to do it each time. And we'll show some examples first in a minute. But this is what you get. Here's what happens. If you have a constant, the Laplace of a constant is 1 over s. Laplace of a constant is 1 over s. That is our result. The Laplace of a constant is 1 over S. And we'll show where that comes from in a minute. Okay. Laplace of a power, t to a power. Okay. That power has to be an integer value. Is equal to n factorial over s to the n plus 1 power, where n is 1, 2, 3, so forth. Laplace of e to the at is 1 over s minus a. Laplace of the sine of a constant times t is the constant over s squared plus k squared. Laplace of the cosine of a constant times t is s over s squared plus the constant squared. Hyperbolic functions, the Laplace of a hyperbolic function kt is k over s squared minus k squared. Very similar. They're related. And Laplace of the hyperbolic cosine k of t is s over s squared minus k. So all of those can be derived. And we'll do that. I'll do a pencast on that so that we can get that. And so when we have a function, right, that we want to do a Laplace on, right, we have to apply the definition. We have to apply the definition. And so that's the basics of what Laplace looks like. There'll be a couple of videos up there on this, so you might want to check those out, and we'll do a pencast to show where these came from. But this is just like a derivative table. Right? Once you have it, you use it. Right? You don't have to use the definition of the derivative all the time. But here is the definition. These are the results of that definition. So you can always use the definition to do this.